The next topic is covariance and correlation coefficient. And we compute covariance and the coefficient of correlation when you have two numerical variables and we expect there to be some sort of association between the two. For example, price and demand. So you expect the price to have some impact on demand. So you want to see whether there is an impact or not, or for example, advertising budget and demand. So when you have two numerical variables and you expect some sort of relationship between the two, we want to compute, well, visual presentation would be to do a scatter plot. You have one variable on the x-axis and the other on the y-axis and plot the points, then see whether the points are clustering around some sort of shape or it is just all over the place. If it is all over the place, that means there is not a relationship between the two. Now, instead of simply relying on visual observation of scatter plots, we can compute numerical measures that indicate whether there is an association or not. And we can compute two of them. One is called covariance and the other is coefficient of correlation. Now, covariance is unit dependent, meaning that if the values are large, then covariance will also be large. If the values are small, the covariance will be small. It doesn't mean that the variability is small because covariance is small. Okay? It's just because it reflects the same units as x and y are represented, whereas correlation coefficient is unit free, and therefore it is more readily understandable. You can readily interpret the value by just looking at the value instead of worrying about the units in which x and y are represented. So let's look at the formula. So this is the covariance formula, and you see the covariance formula is x minus x bar, the deviation of x from its mean, times the deviation of y from its mean, and you sum that, divide by n minus 1 because this is a sample covariance. Okay. Notice that we are not squaring anything, so covariance can be positive or negative. If the variables have positive relationship, then covariance will be positive. If it is negative, for example, price and demand is you expect it to have a negative relationship. As price goes up, you expect the demand to go down. So covariance will be negative in that case. Yeah. Now remember, correlation and covariance, it only talks about associative relationship and not causal relationship. This is not about x causing y. It's only looking at statistical relationships here. Now, covariance will be positive if x and y have positive slope, negative if it is opposite, and it will be 0 if they are independent. I already discussed that. Now, coefficient of correlation is expressed by this formula. You take the covariance and divide by the standard deviation of x and standard deviation of y. Okay, so you can express this. These are the numerator, denominator, denominator. Okay, now r will be a value between minus 1 and 1. It cannot be anything outside of minus 1 and 1. Now the two things we can say about correlation, which is the sign, is it a negative number or a positive number, and the magnitude of the correlation itself. Okay. The sign obviously tells us the relationship, whether there is a positive or negative relationship between the two variables. Okay. So the sign tells us the direction of relationship. The magnitude tells us the strength of relationship. If it is close to positive 1 or negative 1, okay, these extremes, that means the points are very tightly close to a linear relationship or a line. If you draw a line, all the points will be very close to that line. As opposed to if the points are all over the place, the R value, the coefficient of correlation, will be closer to 0, either on the positive or the negative side. So the sign tells us the direction of relationship, the magnitude tells us the strength of relationship, how strong the relationship is. So a number close to minus 1 will be a very strong negative relationship. A number close to positive 1 will be a very strong positive relationship, linear relationship. And a value close to 0 would be weak relationship. So let's look at this in a graph format. So here is an example where all the points are smack on the line. So you get R equal to minus 1 here. So this example tells us where R is positive 1 because there is a positive sloped line and all the points are smack on the line. So here the points are kind of clustered around the line, but not right on the line, and it is negative. So R is more like minus 0.6 or in that neighborhood. Now this example, the points are even further apart from the line, but that seems to be a positive slope. So R will be positive and the magnitude will be smaller because the points are farther apart from the line compared to this graph. Now here is a peculiar situation where you have a straight line where all the points fall right on the smack on the straight line. Yet R is 0. Why? Because here the value of y doesn't change at all irrespective of x. X can be anything, it doesn't matter. So y is always the same number. So that means there is no relationship. X has absolutely no role to play in determining y, and that's the reason why R is 0, and that represents a zero slope line. So now let's look at these computations in Excel. We are now going to compute the covariance and coefficient of correlation between two numerical variables, and we'll use the data from example 3.16 where we have NBA teams and the revenues and the current valuation are stored in this data file, and I have that in the Excel file. So let's go ahead go to the Excel, head on to the Excel file. So we have the teams and revenue in millions of dollars, and then the current valuation in millions of dollars. Yeah. We won't worry about the 1 year percentage change in this example. Okay, now we want to compute, we want to see whether there is a relationship between the revenue that the team is making and the valuation. So we will put revenue on the x-axis, valuation on the y-axis, and then plot the values first. So x and y, let's define x and y. So x is revenue in millions of dollars. So y is current value. So let's do a scatter plot. So when y is on the right side of the two columns, we can highlight both columns at the same time, and the second column will be used on the y-axis, which is good. Otherwise, we have to first insert the y-axis and then add the x-axis values. So we want a scatter plot. So we'll use that one. Okay, there you have it, and then let's go ahead and format it. The x-axis title will be revenue. Okay, so like that. And y-axis is current valuation. And when you examine the scatter plot, you can see that there is a positive relationship, and it looks pretty good positive relationship. There are a couple of points which are way outside as far as the revenue is concerned. And maybe these two are outliers. So we will examine outliers in a later chapter. Right now we'll just simply observe there are a couple of unusual values here. Okay, now we're not going to compute the covariance and the standard deviations from scratch. We'll simply use the Excel function to get these values. So covariance S sub xy is covariance. So covariance, okay, we want dot S, covariance of sample. Okay. And the order in which you give the arrays, data arrays, is immaterial. You can go x first and then y, or y first and then x, it doesn't matter. So that's our covariance, and you see that it is a positive number. If this relationship had been a negatively sloped relationship, this would have been a negative number. Now standard deviation dot S for revenue and then standard deviation stdev dot S of current valuation. Okay. So now the correlation is the covariance divided by the product of S sub x and S sub y. So that will give us the correlation coefficient. And it shows that the sign tells us that there is a positive correlation, and the magnitude, which is really close to 1, says that there is a very strong correlation between revenue and current valuation. And Excel has a function called CORREL, which we can use to directly compute the correlation coefficient value instead of having to compute S sub xy, S sub x, and S sub y, and then calculate R. We can go directly to R by simply using the Correl function. Again, the order doesn't matter. You can give x and then y, or y and then x in the range, and you get, of course, the same answer.